Hey guys. Good afternoon. Oh, hang on. Let me everyone. Yes, Emily. Okay, good. Let's go do some homework problems. Did you guys hear the good news that there might be a vaccine? Hopefully that means we can go back to normal life in a few months. All right, let me just share my screen. Anyone do anything fun over the weekend or watch anything good? I heard there's a good show about chess on Netflix, but I haven't watched it yet. There's a pretty awesome movie about Rubik's cubes, actually. Oh, it's good, Maddie? Awesome. Yeah, I'm gonna try to see if I can get an episode or two in this week. Um, okay, let me just write down. Yeah, if you guys have any questions from the homework, we can definitely go over a few. And then I want to show you today, I want to show you some more ideas about matrices that I think will be easier to follow than what we did like last week. And it will at least give you some more insight into uh, uh, what the determinant actually is and what matrices, what yet another way to interpret matrices beyond like transforming, like changing your perspective. Okay, let's look at 8.3, 8.7, number 38. Um, okay. Um, this is a pretty cool one. Uh, so, uh, so yeah, let's do this one. This is a neat one. This is not one that I would have on a test, but I really like this question because it's a little bit challenging, and you can see that you get a sense from this problem that determinants are uh, really quite deep ideas, and they might show up in surprising places. So this said, show that, and after what we learned today, it'll be interesting to think about, to interpret why this is true, like to have a good intuition for it. But we can do it algebraically. So kind of, and it's not the most insightful answer, but we'll be able to do it. So show that the line through, and this will also be a really good little warm up through x1, and x1, y1, and x2, y2 has equation um, the determinant of x1, And so this is going to be really cool. Today we're going to, by the end of today, we're going to see something that will, first we're going to do this just by um, using the formulas that we already know. And then we're going to do it with x1 and then 1, 1, 1 is equal to um, 0. So let me think here. Yeah. So first, before we approach this one, oh, let me let some other people in. Okay. Hello, everyone. Good afternoon. So Emily asked about this question on the homework. This one is a bit harder, but I think it's a really nice question to go through, and you'll get some cool. There's something really neat that hopefully you'll understand by the end of this lesson. I think it's really a really awesome insight. So we'll do that today, and after we do the first version of this question, we'll go back at the end and we'll see if we can understand it from another perspective. Uh, um, but before we do that, I think I would like to have our next exam, and I'll post the practice, but I would like to do our next exam in a week on Monday. Okay, thanks, Kanjit. I'll post the notes and stuff so she can catch up. Yeah, so I'd like to do our next exam on Monday. I'll post a practice, and you'll see that it's very, it's going to be really straightforward matrix stuff, like some examples of matrix multiplication, maybe one example of doing a Gaussian row elimination. Uh, and then one question with Kramer's rule, and then one or two questions a little bit about the interpretation, the geometry stuff. And I'll kind of warm you guys up and show you what I expect for those. But it's going to be actually a shorter test than the previous ones. Usually it's one of the tests that the students do best on. So, and I'll post a practice later today. I think by the end of tomorrow, you should have enough notes to ace that test, and then we can go over it together on Thursday before the actual test, so we can review it together as well. Okay, is that okay? Does that sound reasonable? Awesome. And I'll make an announcement on Google Classroom right now, so that you guys have that, so that everyone sees it, and reminder. And the other thing is those who those students who I asked to submit corrections in order to take a retake for exam 2, please make sure that it would be great if you can do that before Thanksgiving, before the Thanksgiving weekend. Focus on exam 3, focus on this stuff. But if you have time, please submit your corrections and I'll give you some feedback on them, and I'll let you know if you're ready to take a retake. But I really want those students who didn't pass exam 2 to really think about when they'll be ready to do the retake, because I don't want you guys to push it off too long. I think maximum try to do it the latest, like either right after Thanksgiving, but ideally you can just get it, you can kind of, if you have the opportunity, finish it off before then. And remember, just email me your corrections and I'll give you a feedback and I'll tell you if you're ready to take it, and we can schedule a time. Okay. So first, let's approach this one. The first thing is, how do we find the equation of a line without matrices, just regular stuff? What do we do to find the equation of a line through x1, y1, and x2, y2? Does anyone remember? And if you know this, make sure I recommend just try to do it right now in your notebook. So I'm going to just draw it. And those of you who don't know this off the top of your head or not sure how to start it, here's a really valuable picture to think about. Here's x1, y1, and here's x2, y2. And this is kind of abstract, but we're thinking of x1, y1 and x2, y2 as like actual numbers. So we're using letters, but we're thinking of them x1, y1, x2, y2 as like constants. And the variables are really just, these are the variables, and these are like our constants. All right. So what do you think? Anyone want to explain or give me give us a starting point? What we can calculate first? Archer, what do you mean? Calculate x1, y1. Well, I should clarify here. We're given x1, y1 and x2, y2. That's kind of like we're given those values. So we don't care what they are necessarily. We can write them. We're just writing them as x1, y1. But think of those as numbers that were given to us. And we need to find the formula using those values that were given to us. We need to define the equation of the line that goes through them. So like if I gave you like example, if I gave you, for example, whoops. If I gave you, for example, 3, comma 1, and let's say over here it would be 7, comma 5, you know, what do you do to figure out this equation? But don't do 3, 1, 7, 5, do x1, y1, x2, y2. So what's the first thing you would do? And this is kind of a good review of equation of line stuff that we did in the beginning of the course. Anyone remember? What could we calculate here? Nice. Gabriele, what do you suggest? Let the class know.
Oh, I said define the slope.
Perfect. Awesome. Nice and perfect. Exactly. Yeah, let's do the slope. And it's easy. It's like very simple to do it when you have the numbers. But when you have the symbol, you're using kind of letters to represent constants. It's still not that bad. And yes, you got a good formula there. It would just be the slope m is equal to y2 minus y1 all over x2 minus x1. And I just think of this thing as like a number. This is some number that now I can use. It has letters in it, but whatever. It represents to me a number. It's not a variable. Okay. Anyone want to suggest what we can do from here to quickly write down the equation of the line? And we did this strategy a little bit in the beginning of the course. Sometimes there's two ways to do it, but there's one way that makes it a little bit easier. Does anyone remember what we can do here? And now we're going to have a variable x and y. Those are considered variables. Anyone remember what would you do if we had like if we found the slope? What did I write? I should have erased it. 1, 3, 1, and 7, 5. So once you find the slope m, where do you go from there to find the actual equation of the line? And here the slope m is actually equal to the number 1. What do we do next? Anybody? And don't worry if you're wrong. I mean, it's totally. What do you mean assign y2 and y1 and x2? Oh yeah, yeah. Oh, so okay, yeah. So what I mean is like when I wrote 31175, um, like imagine we didn't have x1, y1, all that stuff. You solve the slope. Where do you go from there? Once you have the slope, in this case, the slope is going to be 4/4, which is just 1. Um, what steps would you take to get the equation of the actual line, that orange, that yellowish line? And then we're going to try to do the same steps, but we're going to do it abstractly with x2, y2, x1, y1. But just let's do it first with a number. Does anyone remember? Oh, that's okay. That's okay. Yeah. What could we do? Do you guys remember the two approaches? There's the approach where you can try to solve for the intercept. So we know the slope, right? So we know the equation is equal to y is equal to 1 mx plus b. We just found m, and we can do this, and we can solve for b. Please hit yes if you remember this approach. Nice. Oh, Emily, it's 1 because I did 5 minus 1 rise over run. So it comes out to 4/4. Even though graphically my picture is not drawn to scale, this vertical piece is 4 and the horizontal piece is also 4. Yes, Emily, you're right. We are doing it abstractly. I'm just doing a concrete example to help us remember the steps, how to do it abstractly. But you're totally right. The actual slope would be the abstract formula for the slope. The general formula is that. Okay, so this is one way to do it. Does anyone remember, how do we do point slope form? There's a general formula for point slope form. Does anyone remember it? Uh, it's not a standard form. I think is mx. Yeah, that's not exactly it. Point slope form tells you if you have a point and a slope. Like in this case, we know 3, 1, and we know m equals 1. So we know it's got to go through this dot and it's got to have this slope. So we know the line. So what you can do when you have that is you can get a nice equation. You can write it like this: y minus the coordinate, the y coordinate of your point, equals m, which in this case happens to be 1, times x minus 3. The general formula is y minus y1 is equal to m times x minus x1. And if you think about what this means, all it's saying is that if you have a random point, xy, anywhere on the line, like over here or over here, let's say, it could be anywhere, right? Who knows where it is? If you look at what this expression is saying, this expression is saying the ratio of y minus y1 to x minus x1, so the ratio of the vertical leg to the horizontal leg, if xy is over here, it's like that, the ratio is equal to the slope. That tells us that, oh, hang on, we have a bunch of similar triangles, so that tells us anywhere we pick an xy that satisfies this equation, it's got to be on the line. Yeah, yes, so this question is a little bit strange. You'll see in a second what the matrix for now has nothing to do with it. We're doing everything for now. We're actually just finding the equation using what we learned about equations of lines. Okay, how many of you feel comfortable with this formula? Please hit yes if you feel comfortable with it, and hit no if you're not comfortable with why I wrote this formula down. This is just from equation of line. And let me know if you have any questions about this. I'm happy to discuss this formula more. But this is called point slope form. It's really handy, by the way. Point slope form is super easy because you don't need to go through this process to solve for the intercept. If you have a slope and a point, you can just plug it in and you immediately get a nice equation. And if you want to solve it for y, you can move the number over to the other side, and then you can also get it back into mx plus b form. You just have to do a little bit of algebra. Okay, so you guys were okay with this. Look good. So now, what we're going to do is we just we express m using this formula that we got earlier. Now keep in mind, our true variables are y and x. Everything else is kind of like a constant. And let's write it in mx plus b form. So we have y minus y1 equals y2 minus y1 all over x2 minus x1 times x minus x1. This looks really complicated, but this is just point slope form. And this is just a number. This is just some number. This is just some number. This is just some number. These guys are variables. This is a variable. This is a variable. Okay. Now let's rewrite this we're just going to rearrange everything and set it equal to 0 because we see this equation has everything equal to 0. So when I do that, I get the following. I'm going to expand everything and I get y minus y1 times x2 minus x1 equals y2 minus y1 times x minus x1. And then I can move everything to the other side and I get the following. Y minus y1 times x2 minus x1 minus y2 minus y1 x minus x1 is equal to 0. Okay, so I'm going to stop here. If you can FOIL these expressions out, and what's cool is you'll get a pretty long expression. And what you can do is say, oh, look, this whole thing, when you expand it out, has to equal to 0. But look at this. Look at what this is saying. Why don't we take the determinant of this matrix and set it equal to 0? So for homework, see if you can double check that when you take the determinant of this thing, and you can either do it by the Candy Crush method, or what I would do is probably just write x, x1, x2, y, y1, y2, and just do the diagonals this way being added and the diagonals the other way being subtracted, and you can double check that expression that you get is going to have a bunch of terms because there's a lot of different letters and subscripts. It's going to have a bunch of different things, but you can check after you FOIL this out that it's going to be exactly the same thing. So I'm just going to stop there in the interest of time, but do you feel like you could complete the rest of the problem? Please hit yes if you feel like you kind of know where to go from here. And no if you feel totally stuck still. Okay, Emily, can I ask where do you feel a little bit shaky, or kind of where could I give some more insight? Okay. So you're okay with kind of how we got to this? Oh, you didn't hear. Okay, sorry. Okay, yeah. The next step is just comparison, matching things up. So it's actually really straightforward. It looks complicated, but it's really straightforward. You expand this whole thing. This is by the way, these guys are being foiled. You foil these together. You see there's a minus sign though. So just be careful with foiling with minus signs and stuff. You FOIL that out, and you're going to get a bunch of different terms. And so you're going to get a complicated expression with a bunch of different terms. Now, the game is, well, do the determinant here. We know the pattern for determinant. You can do either way that you like. And then what you see is that when you expand this determinant, you're going to get exactly the same expression as if you did this. And that will conclude, say, oh yeah, these are the same equations. Now, do you guys think, do you feel like that gave you a lot of insight into why the heck the determinant is related to the equation of a line? How many of you feel like now you understand it, and how many of you feel like it's just because of the formula working out that it, it's like, okay, well, it works out. I would argue from this kind of from this description, it's kind of like, well, yeah, the formula works out, and I understand the equation of, I understand this equation. This I can understand because I have a picture, right? I know what this represents. This is just slope, and then you just having a bunch of similar triangles. So this I understand. But then why the heck, what does that have to do with a determinant? But sure, it can work out. I can do it by hand and see that it is the same thing, but it's kind of mysterious. Like, what the heck? Why? Like in math, sometimes you learn things and say, oh, here, I did it. The formulas are the same, but then it's like you have to ask yourself, wait a second, do I actually have understanding of it, or is it just, did I just see that the formulas work out, but I don't have no idea why they work out? Like, how the heck did somebody wake up and say, oh, try this determinant, it'll give you that equation? Like, nobody's going to wake up and think of that, So let's move forward, and we'll see a little bit, hopefully by the end, you'll see another way to understand this idea, and it's really, really nice. Okay, so Emily, thank you for asking that question. I'm glad I got to talk about it. Now I'm gonna shift gears a little bit, and we're gonna do a little bit of geometry. So yeah, let's first talk about yeah, we might yeah, let's first talk about geometric transformations. Transformations of the plane. Okay. So let's see here. Ivan, what are some geometric transformations of the plane? Anyone have some good examples? Just like, what are and you learned these probably in middle school, early high school. What are some of the things that you can transform? What are the things that you can do to shapes?
Dilation, reflection, rotation. There's the movement one. Where is it shift?
Dilation. Yes. Sorry. Archer said rotation.
Yes, rotation.
Rotation. Shift is translation.
Reflection.
And then reflection. Nice. Awesome, guys. Am I missing any of them? Yeah, so those are the main things that we can do. So it turns out that matrices are actually really, really good at doing these things, and we can think of a 2x2 matrix as essentially doing all of these, except what it doesn't do is it doesn't do the shift, which is translation. But we can think about matrices as doing all of these operations. And instead of thinking of them as acting on a single shape, we could think of it as doing it to the entire grid. So we can think of like the entire grid being dilated, the entire grid being rotated, and the entire grid being reflected over some axis. So we can actually do all of these and express all of these transformations using a 2x2 matrix. And there's another one called shear, which is not one that is not one of the rigid transformations, but a shear transformation is one where have you guys ever messed around with these like I guess have you ever messed around with the drying rack? Like a folding drying rack? How many of you have ever like there's other shapes, I'm trying to think of it, but a drying rack is kind of like an example. Have you guys ever unfolded and folded a drying rack? Yes, if you have, or if you have. No, if you have, never, not. You don't know what I'm talking about. Wait, a lot of people haven't. So a drying rack, have you guys ever seen these drying racks? Like the wooden ones? Like that? A lot of people haven't seen them. You know, you put your clothes on here. I have one for my wetsuit. Oh yeah, some people have. Well, okay, so the thing with these drying racks is you can fold and unfold them. And one of the transformations that you do is you can turn it, like you can turn the, like if you look at it from the side, these are like wooden sticks. You can basically turn the grid, you can go from like a parallelogram to a rectangle, and then also you can make the parallelogram if you want. If you want to fold it all together, you can turn it, like you can transform it by squishing it together. You can do something like it makes it more of a skinny diamond, essentially. It even kind of folds, kind of, you know, it'll fold flat, essentially. Or even you can even think of a little bit like an accordion. So that's the idea of shear is you have a rectangle, and if you can transform a rectangle by kind of like sliding the top and pushing it to make it into a parallelogram. And you can combine that with a dilation in one direction as well. So it's basically just turning rectangles or squares, turning squares into parallelograms. So that's it's not a rigid transformation, but that's something else you can do. Okay, but let's talk about. So that's just a little bit of an aside. So these are the transformations that you can do with a 2x2 matrix. So these are a special class or a special group of transformations that are that can be represented easily, very easily, as a 2x2 matrix. And here's how we do it. And we're going to make a really nice observation. So if we want to transform something, what we notice is the following. So here's my x-axis and here's my y-axis. And I'm going to write something here that's going to describe what I call the standard basis, or what's called the standard basis. So it's the standard basis is our two vectors that point, one in the direction one step going right and the other one in the direction one step going up. And I call them E1 and E2. And if you want, you can sometimes, to make sure that you know it's a vector, you can put a little arrow on the top. So E1 is really simple. It's just the vector 1, 0. And E2 is the vector 0, 1. Okay. You could do something in higher dimensions, but we're just going to stick for now in two dimensions. So in particular, if you want to tell me how to get to any point in the plane, you can always tell me, like, if I want to know how do I get to this point is 3, 5. How do I walk to there from the origin? Well, that's going to be 3e1 plus 5e2. Walk 3 steps to the right and 5 steps up. So let's take a look and think about what a matrix does to points, or what a matrix does to E1 and E2. So let's examine, just explore a little bit, what is the matrix 3, 0, 0, 3? What does this matrix do to E1? Can anyone tell me? So if you want, you can write it 3, 0, 0, 0, 3, 1, 1, 0. So what is the result when you take this matrix and you multiply it times the vector 1, 0? So do the trucks into the parking spot. And message me when you got this one. And this stuff will be on the test. It'll be some kind of basic understanding of geometric transformations and how to use matrices. Nice, Jack. I'll wait for a few more people. Oh, it's just going to be, so this is a 2 by 2 into a 2 by 1, right? This is 2 by 2 here, 2 by 2, and a 2 by 1. So the result is only going to be if you do the first truck into the parking spot, there's only one parking spot. So the result will only have one column. So we do the first truck into this parking spot, and then we do the next truck into this parking spot. And if you recall, the other idea that we had, it was like you can interpret matrix multiplication. There's another way to interpret it, is you can take one of these columns plus none of these columns. So do you see that this will be actually just the first column, not you don't want the second column. So let's do it together. And stop me if if you have any questions. So the first thing we do is we do the first truck into here. That's going to give me 3 times 1 and 0 times 0. And adding those numbers together, I get 3. The next one will be I'll highlight this in orange here. That's 3. The next one is this red truck into the same spot again, but this time it's just going to be 0. Okay. So this just takes the vector 1, 0, and it maps it to the vector, which is just 3 times E1. Because I can factor out the 3 here. This is really 3 times 1, 0. This is really 3 times E1. So what this moved to is E1 got mapped over here to 3E1. Okay. What about E2? So can you guys tell me what happens if we do multiply this matrix times E2? What do you think that would do? What would the result be? Do the trucks into the parking spots again. Anyone see what happens?
303.
Exactly. Nice. And we're going to do another example, and then you'll see exactly why this pattern happens. But when you do the trucks into the parking spots, you'll see that you only get this one basically just picks off this column. But you can do it carefully with the trucks. It's really good to do it with the trucks and parking spots. So you go here first, you get 0, and then the second truck gives you a 3. So it gives you 0, 3. And say, okay, cool. So what that does is it moves the E2, it moves it, so let me draw it here. This E1 got mapped to here, and this E2 got mapped to over here. So this is going to be 3, 8, 2. Okay. Nice, Gabriel, perfect. So this is a vector, and then this one also. It's nice to put a little arrow over the vector so you kind of remind yourself that it has 2 coordinates. Okay, so now let's just do another general example, which is let's do 3003 times just a random point A, B. Can anyone tell me, just by looking at this, what does this do to the vector AB?
It times it by 3.
Exactly. Awesome, right? It multiplies it, moves it to 3A. When you do the first truck into the first spot, you get 3A, and the second truck in the second spot, you get 3B. And another way you could have seen that is to break up AB by saying AB really represents moving to the right by 3A steps and moving up by, so you can do you can break it up into a sum like this, A E1 plus B E2. And when you multiply this matrix out, what you'll be left with is, because these are just numbers, but yeah, what you'll be left with is 3A, 3B. Or in other words, 3 on the outside times the vector AB. Okay, so what do we observe here? What this matrix does is we have our original grid. And to understand what the transformation does, we just need to understand how does the fundamental parallelogram, which is the one that we get from E1 and E2 as our kind of edges, how does that shape change? And if we can understand how that shape transforms, then we can understand what the transformation is. So that's the idea, is that the matrix, the first column of a matrix tells us what happens to the E1 vector, and the second column tells us what happens to the E2 vector. If you draw the picture and you think about what happens in general, you can understand what the transformation is. So this transformation, it moved the red arrow, it scaled the red arrow by 3, it scaled the green arrow by 3. Because of how matrix multiplication works, it will actually scale, it'll do the same pattern to any other vector. It'll just stretch every shape by a factor of 3 from the origin. So I can extend the grid here like that. Any questions? Do you guys see kind of, are you seeing a sense of how the columns of a matrix represent what happens to E1 and E2? Is that okay? Any questions here? I see a few people said no. Archer, where can you ask where you have a little confusion, because I know this is a little bit abstract. Oh, okay. You got it. Okay, cool. Okay, let's do another example. I think let's do another example, and I think as we do more examples, hopefully the mechanics and the idea becomes really clear, because it looks complicated, but you'll see is if you understand how coordinates work, like up, down, left, right, this is nothing much deeper going on than beyond that, and describing how things transform. That's it. There's nothing else that's exciting. Okay, let's do something really cool here. Let's describe use matrices to describe a 90-degree rotation. So how do we do that? So question is, so use a matrix to describe a 90-degree rotation. And so here's the idea. 90 rotation, everything we do, by the way, is around the origin. So the origin never moves. That's the key with these. And so the thing about matrices and the thing about these transformations is, if you tell me how the transformation affects E1 and E2, you guys see that if I know how my piece of paper moves overall, by telling you how the green arrow moves and how the red arrow moves, then I will have a new grid. And then because I have a new grid, I know exactly how everything on my piece of paper must have moved to the new paper. So all we need to focus on is to describe a matrix or to describe a transformation. All you need to actually describe is how does E1 get affected and how does E2 get affected. And then once you understand that, then you'll see, oh, now I have a new grid because I have a new E1 and a new E2, and therefore I can figure out which points correspond to which ones from the old grid to the new grid. That's just the idea. And it's similar to what we did previously, where we talked about changing the grids, but now it's thinking about it in terms of just transforming the original square grid to a new, doing some simple transformation to the original square grid. Okay, let's do a 90-degree rotation. So I'm just going to draw a picture, okay? So here is, I'm going to do green and red again. E1 is right here, E1. And E2 is right here. Okay, what happens to the green arrow? Which way does the green arrow, if I do a 90-degree rotation, let's do it, let's make it a clockwise, no, counterclockwise, sorry, counterclockwise. We can do either one, but let's just do counterclockwise. So what happens to the green arrow after I transform it? And I'm going to do an arrow, and I'm going to write A or T. I'm just going to write A to represent that we're putting the green arrow, and we're going to do something to the whole thing to move it 90-degree counterclockwise around the origin. What happens to the green arrow? Where does it move to? It becomes E2. Nice, Conjit. Perfect. So I'm just going to draw it here. I'm going to write the x-axis again. X and Y axis again, but now I'm going to write, I'm going to put the green arrow, I'm going to write here A, E1. Rather, this is what happens to E1 after I moved it by applying the transformation A. Okay, what happens to E2? What happens to the up arrow? Where does it move if you rotate it 90 degrees counterclockwise? Nice, it moves, it points to the left. That's it. That's all that's happening. Pretty simple, right? This is A, E2 arrow. Do you guys see, can you visualize that if you had that grid, like if you use the red and green arrow to describe the fundamental building blocks for a grid, we call, by the way, this is called, this type of grid, where you make the grid by taking integer amounts of E1 and E2, and you draw a nice little grid of rectangles, or squares rather, that's called a lattice. And it's just because it's like got a bunch of, it's a grid, it's a grid, a lattice is just a grid, that comes from integer or whole number amounts of some initial vectors. And so you can imagine, like, yeah, if E1 and E2, if you rotate your entire piece of paper, then the entire grid, E1 gets moved up, E2 gets moved to the left, and the entire grid moves along with it. That's the key idea. Okay, so here's how we do it. In order to describe a matrix, we want to know what is the 2x2 matrix that does this. All we need to do is figure out, because I'm just going to make a little observation here. If you ever multiply A, B, C, D, and you want to see what happens to E1, if you just do the truck into parking spot, look what happens. When you do the truck into this parking spot, you get A, and when you do the other truck, in the second truck, you get C. So it's really nice. Whenever you multiply matrix times 1, 0, you get this first column, AC. And similarly, if you multiply a matrix A, B, C, D, any matrix, any 2x2, times 0, 1, all it does is tell you the second column. So what this tells us is if we want to build a matrix that accomplishes what we're drawing in the picture, we need to tell it, we know where E1 goes, so therefore we can design our matrix so that the first column is the result that we want. So the first column will just be, in this case, we want the first column to be AE1, which would be 0, 1. So this is going to be just AE1. So I basically, because I know where E1 goes to, I intentionally put that as my first column. And my second column will be AE2, where I want it to go to. And that vector, can anyone tell me what the coordinates are for AE2? So what should I put? What should I put in this column? Not 1, 0. Where does this vector, what are the coordinates of this one that points to the left? It's close. It's not 1, 0, but it's negative 1, 0. Perfect. So it's going to be negative 1, 0. So this matrix, 0, 1, negative 1, 0, this represents a counterclockwise move. Counterclockwise 90-degree move. All right. So essentially, anytime you see a matrix, you can immediately, if you look at the first column and second column, and you interpret them as, oh, this is how my grid is changing, you can start to understand 2x2 matrices as just transformations of a piece of paper. That's all. Okay, let's do another example. What would I do if I Oh, okay. Let's just check one thing here, by the way. What happens? Can anyone tell me what would happen if I rotated the number, the coordinate 2, 3, 90 degrees? So let's do it with a matrix. So let's investigate an example. So this is let's try an example. So what if I do 0, 1, negative 1, 0 times 2, 3? Can anyone tell me what that is? If I do 2, 3, it would be yeah, 0 times 3, negative 1, that would be the first number. Yeah, what happens if I multiply that matrix into this vertical, into this vector? And also, by the way, jump in, because this is a new topic that I think many have not seen. So jump in if there's any step, like even the most basic thing that it seems you don't understand, just ask me. I'm happy to kind of go over it. Nice, Gabrielle. Oh, Gabrielle, what did you get and how did you do it?
Wait, did you say me?
Yeah.
To like explain? Okay.
Please.
Okay, so I did the truck parking spot thing for the first one.
Uh-huh.
And after doing the truck parking spot thing, I got 0 plus negative 3.
Nice.
Which equals, wait,
Yeah. Negative 3.
Yeah, which equals negative 3. And then I did it for the bottom one too. And I got 2 plus 0, which equals 2.
Excellent. So you got that this point, that this thing got moved to this vector. Let's investigate that on the picture and just make sure that it works out, that it satisfies what we expect. So 2, 3 is going to be, let me draw it in purple. Or yeah, let's do purple. 2, 3 is over here, right? This is up to over 3. Now, what it's saying here is move it over to negative 3, 2. So negative 3, 2 is over here. This is what? One spot, 1, 2, 3. Negative 3 and up 2 is like over here. What do you guys think? Does that look like a 90-degree rotation? And it's the same vector? Hey, yes, if you believe that the purple line looks like the purple line got moved 90 degrees. And hit no if you feel not sure what's going on. Oh, it looks like indeed. You know, this one, you see it got moved from here, and I'm going to draw it on the same piece of paper. It got moved from here to over there. It would go on a little bit. By the way, what is the slope of the first purple line? Can anyone tell me what the first slope is? Go over 2 and up 3. What is the first slope? What's the slope of this arrow? If it's, you know, 2 comma 3 or 2 over 3. How do we find the slope of this one? Anyone remember? So how do we find the slope of this purple one? The slope here is rise over run, right? It's 3 divided by 2. So this slope is 3/2. This slope here is again rise over run, but it's the slope is going down. So the rise is actually going to be if you go from left to right, the rise is negative. It's -2 over 3. And do you guys remember? So this slope is, I'm just kind of pointing it out here. M, the slope is 3/2, and here M is equal to -2/3. And we've learned in the past that when two lines are perpendicular, their slopes are negative reciprocals. So this is consistent with what we learned before. Okay, any questions at all on any of this? I'm happy to explain any of it or go through any step again. Do you feel like it made sense, kind of what we did? That we're trying to describe a transformation, and the shortcut that we're doing is we only need to focus on what happens to E1 and E2. Okay, let's do another one together, and then I'll ask you guys to do some ones on your own.
Then the -3, 2 is the answer for what would be?
Yes.
Or, okay.
Yeah. Or the -3, 2 is the answer when you multiply 0, like when you multiply that matrix, when you multiply this matrix times 2, 3, you get -3, 2.
And is it always going to be 0, -1, 1, 0, or?
If you wanted to represent the transformation of rotating something 90 degrees counterclockwise. Did that was that what you were going for?
Yeah, I was just trying to clear that up. Thank you.
Yes, and we're going to do another one where it's going to be a different matrix. So let me give you another example, and ask you guys to see how you can come up with it. Remember the strategy. I'm going to ask you to transform the piece of paper, the original plane, and all you need to do is think about, oh, how does this change E1 and E2? If I understand that, then I can put those results into 2 columns and call that my matrix. That's it. That's all you got to do. Okay, so here's a simple transformation. Write a matrix and we'll see something kind of neat at the end as well. We'll see a few things neat, and we'll continue this tomorrow as well. Write a matrix that represents a reflection over the x-axis, or in the line. If you want, you can say in the line y equals 0. Okay, so let's draw our grid. And we're just going to do some simple transformations. Later, when you get to trigonometry, you'll be able to do more complicated transformations like rotate by any angle, or reflect in some sort of special line or something like that. But for now, we're just going to do some really simple ones. So first, I draw two set of axes, one that represents my original paper, and one that represents my transformed paper. And I always draw E1 in one color, and I draw and label E2 in another one. And after I apply my matrix A, imagine the left side is my piece of paper. After I apply the matrix A, I'm going to observe what happened to my piece of paper. And then I'm going to use this observation to be able to write down the actual 2x2 matrix that represents that A should be. So yeah, what happens to E1? Can anyone tell me? Can anyone say what happens to E1 if we? Are you sure? Could you that? I think you're on the right track. But what happens to E1? If I reflect if I have a piece of paper and I reflect it over the x-axis, what happens to the green arrow? And it's more fun in person when I do this, or because I can't do it on the do it on the actual piece of paper. But what happens to the green arrow if I have a piece of paper and I reflect it horizontal, like over the x-axis? What do you guys think? Nothing happens. It stays where it is, right? The green arrow doesn't move. So I'm going to write that in. The green arrow stays where it is. This is AE1. Okay. And Kajit, do you want to share what happens to the red arrow? Nice. Yeah, let everyone know. What do you say?
It points down.
It just points down. Everyone okay with that? So this is AE2. Okay. And now we can write our matrix that represents this. And it's a very systematic thing we can do. We have our 2 by 2 matrix. The first column is what happens. We want to express where E1 goes to. This is where E1, where does E1 go to? So I'm going to write here the result of AE1. And over here, I'm going to write the result of what happens when I do it to E2. And so the general matrix will be 1, 0, 0, minus 1. This is equal to A. Can you guys see visually what this is doing? We're taking the grid and we are just flipping it over. That's it. And because of like how matrix multiplication works, because it's distributive, it does the same exact operation to every other dot on the grid. That's really the key observation, is that matrix multiplication, the way the trucks into the parking spot works with a vector is it's distributive. So if you have some number of E1 and some number of E2, and you know how each of those gets manipulated or gets transformed, you do the same exact pattern to any other point on your grid. How do you guys feel about this transformation? Does it make sense, what I wrote? That this represents flipping something over the x-axis? Please hit yes if this is starting to make a little sense, and no if you're still a little bit lost. And or a coffee cup if you're checked out. Okay, try to follow the next one. Those of you who are checked out, is there anything I could explain or any idea that might clear it up, or which part do you find kind of most confusing? And let's also just to kind of do another example. So here's an example. If I do 1, 0, 0, negative 1 times 3, 5, just a random point. When you do the trucks into the parking spots method, so truck into the parking spot here is going to be 3, and this one would be negative 5. So what it does to that arrow is it takes 3, 5, and it just moves it to 3, negative 5. And that's exactly what we wanted to do when we flip something over the x-axis. Okay. All right, let me ask you guys to see if you can come up with the matrix. So find the matrix. That rotates 180 degrees around the origin. counterclockwise. It doesn't really matter because it's 180, but I'll just write it counterclockwise. Okay, I'm going to ask you guys to do this one. And message me when you're done. Message me if you have no idea at all where to start also. I'll leave the other picture up. Okay, so a good place to start is you should always start off with just with these guys. Just start off with a regular picture, and then ask yourself, okay, when I do this transformation, after I move it around, what happens to my green arrow, and where does my red arrow move? And then you can just to express the matrix and actually represent it, all you need to do is express the coordinates of the transformed E1 as the first column and the coordinates of the transformed E2 as your second column. That's it. So first step is draw E1, E2, just like regular left going right, going up vector, simple vectors, and then do the transformation on your plane and keep track of what happens to the green vector and what happens to the red vector. Archer, a little bit off. If we want to rotate something 180 degrees, and as you're doing this, I like to really visualize, like when I'm going from this picture to this one, I really like to visualize like actually flipping it over, because I can see, you know, the nice Kanjit, nice Allison, great job guys, nice Archer, you got it. Allison, would you care to just kind of give us a quick picture and explain how I can draw the picture, but do you want to just tell us kind of what you did?
Okay, so so for the first one, I did the normal graph thing, and then I put E2 going up. And then I put E1 going the other way, like on the x-axis. And then when I flipped it, E1 was just like opposite, so it was going towards the negative direction, and then E2 is the same. It was going towards the negative.
Exactly. So you rotated it, every arrow gets rotated 180, which means it just points opposite.
Yeah.
Perfect. So it's like, I'm just going to draw a little arrow here, like just imagine everybody getting rotated. Like that. Awesome. And so how do you know the matrix then?
Because when it's the second graph, E1 is facing the -1, but it's still on that 0 line. Wait. Yeah. Okay, I think I'm probably explaining this weird, but it's still on the 0 line, but then it's at 1, and then
it's still on the x-axis.
Yes. And then E1 is still on the y-axis. E2 is still on the y-axis, but then it's just on the 0. It's like at 0, and then it went down 1.
Perfect. So what's the coordinates of what happens? The new green arrow, what are those coordinates?
-1, and then under it's 0.
Perfect. And what about the red one?
0 is on top, and then -1's on the bottom.
Perfect. And look at what matrix we have. Does this look like a familiar matrix?
Yes.
Which matrix does it remind you of?
The 90-degree one? Wait, no.
It's, I mean, okay, a lot of these matrices so far have 1s and 0s. That's true. But this one in particular is very special. It looks a lot like something else that we've seen. Not exactly, but there's one matrix that we saw that I've talked a little bit about that looks like this one. I think I gave you the name of it. What if I take it, similar to Cramer's rule? This is if I take out the -1 out of the entire matrix, so put that number on the outside of everything, what I'm left with is 1, 0, 0, 1. Do you guys see what matrix? Do you guys remember the name of this thing and where this showed up? It started, I think I told you, it started with an I. ID. Maybe I didn't say it. I don't know. Yeah, so this showed up. You remember when we were doing row reduction or Gaussian elimination? With the pivot stuff, we tried to turn our original matrix into one with 1, 0, 0, 1. I said that this was somehow a very special matrix. It was called, do you guys remember this was, maybe I didn't say it, I don't remember off the top of my head, but we call this the identity matrix. Does that ring a bell, or is that, did I not mention that? I don't remember.
I kind of don't think you mentioned that.
Okay, so yeah, this is called, but you remember we tried to, we were trying to make that shape or make that matrix when we're doing the row reduction. We're trying to get one that has 1 on the diagonal and 0 off the diagonal. So this shape is called the identity matrix. And what the identity matrix does is, let's think about what this does. It's really, really nice. What does this vector, what does this matrix do to E1? So in other words, where does it send E1 to? What's the first column in this matrix? What happens if I multiply this matrix times E1, where does it map it to? So if I multiply 1, 0, 1, 0, 0, 1 times 1, 0, whenever you multiply times E1, you just pick off the first column. So this just sends it to 1, 0. So this just keeps 1, 0 at 1, 0. And if I do the same thing to 0, 1, I should write it better. So 0, 0, 1, this would just be 0, 1. So can anyone volunteer and say what happens to the grid if I keep E1 at E1 and E2 at E2? What am I really doing to the grid? I'm doing nothing. I'm keeping the grid as it is. So that's why we call it an identity. It's essentially the same thing as just multiplying by 1. You're keeping everything where it is. If E1 doesn't move and E2 doesn't move, then the whole thing doesn't move. Now, what's cool about this matrix is what does the -1 on the outside represent? That's just a scaling factor. So if you ever have a vector, AB, and the transformation you apply looks like the identity matrix, but maybe with another number on the outside, you can pull that number out, and you can think of it as just multiplying your vector times your entire vector, multiply every coordinate times this number. And so, for example, if you have a vector like, let's say, let's do one over here. Let's say this vector is 4, 1. If you multiply everything by -1, you're going to be over here, -4, -1. So basically, what you see is that when you rotate something 180 degrees, is it surprising that it's the same as just multiplying the entire vector by -1? Right? You're just pointing in the opposite direction. That's all we're doing. It's just a fancy way of doing that. And the other thing is, look at the original problem that we did with the dilation. Do you guys recognize, now that we went over that, what's another way to interpret this vector? Or this matrix, sorry. Does this look like the identity matrix, kind of? Do you guys see that you can factor out the 3, just like a overall number, and what you're left with is the number 3 times the identity matrix. So it's saying keep everything fixed where it is, and then multiply everything, every coordinate by 3. And we know that what that does essentially is it dilates our shape by a factor of 3. How do you guys feel? You guys did a great job kind of, oh, last thing. I'll let you guys go after this last example. So this is the most important thing. I encourage you to please read over these examples so that you understand what we're doing and why how I got to each matrix A. So make sure for homework that you read over and you understand what the heck is going on in these nodes. Because I might ask on the test, like, describe the following transformation using a matrix, and you have to do the same steps. But now let's kind of do one last thing. We saw that the matrix for a 90-degree rotation, I'm going to write it R90. We saw that R90 equals 0, 1, negative 1, 0. This was what we saw earlier. Where was it? Yeah, we saw it here. So this guy. So 0, 1, negative 1, 0. So this was from earlier. Can anyone tell me, let's just do this last thing. What's R90, the matrix, using matrix multiplication times R90? Please just do this really carefully using the trucks into the parking spots and tell me what you get. So this is good practice of trucks into parking spots. And this will be the last thing, and then I'll let you guys go after this observation. And this is kind of the heart of this idea. That's really neat. And then tomorrow we'll discuss some stuff with determinants. So I'll give you guys a few minutes to do this, and message me when you got R90 times R90. You should get, because it's a 2 by 2 times a 2 by 2, what you remember is that the middle dimensions cancel out. So the result, if you have two trucks into 2 spots, you'll actually get 4 numbers. You'll get another 2 by 2 matrix. So the answer should be another matrix. So let's do the first truck. First truck into the spots. These are our 2 spots. So the first truck that we get, anyone get the answer yet? First truck into the first spot is going to be 0, 0, negative 1, 1. That's just going to be negative 1. And then, nice, Hannah, excellent. Archer, very close. Oh, Hannah, you got it, awesome. And then the first truck, the orange one, into the second spot, like this. So this guy into here, the zeros match up and the negative 1 and 0 match up. So those just multiply and give you overall 0. So that's going to be 0. And then let's do another, the second truck for the second row. We get 1, 0 parking into here. The zeros and the numbers kind of cancel, like they sync up. Each 0 hits a number. So overall, you just get 0 there. And over here, you get 1 times -1 plus 0 times 0. So we get this matrix. Last question. What is this matrix? What does this represent? What did we just see? Nice, Gabriel. What is this last matrix here? Where did we just see it? Oh, this is not exactly the identity. It's the 180 matrix. The identity matrix, sorry, I should have made that clear. The identity matrix is similar to what we saw. The identity matrix is just this one. But what we saw previously was -1 times the identity matrix, which is actually the 180-degree matrix. This is the R180. And so this is the main idea for all of this, is that a matrix represents a 2x2 matrix, represents a geometric transformation, somehow moving your piece of paper in a way so that the grid, everybody who's on the grid, moves along with the grid. So either you can do dilation, you can do reflection, or you can do rotation. That would keep the grid as it is. So you're not like ripping anything up. You could, so that's the idea. And the other key idea is that if you want to, so every transformation has a matrix that it's associated with. If you want to do a transformation and then do another transformation after it, for example, if you want to rotate and then flip your paper, you can represent that by doing one matrix first for the rotation and then multiplying, using the trucks into the parking spots, you can multiply that times the other matrix. So what matrix multiplication really represents is a sequence of geometric transformations. And next time we'll see how that idea could help us do really, really big matrix multiplications without actually doing any trucks into parking spots. And you'll start to get an insight into another perspective and a nice insight into how shortcuts with matrix multiplication. Any questions on this one? Well done, those of you guys who volunteered. Thank you for answering the questions, and I think you guys all did great with the responses. Are there any questions at all? All right, guys, I'll see you. And Hannah, I got your comment about the homework. We can maybe go over that tomorrow for sure. Just please ask me before class. All right, guys, I'll see you next time. I'm here if anyone. Bye. I'll be here for a second if anyone has any questions, but otherwise, see you guys tomorrow.